The divergence theorem is of general mathematical validity, and it applies to any vector field. In particular, it can be applied here in electrostatics to the electric field strength E and the electric flux density D, relating these two vector fields. The divergence theorem allows us to express the first Maxwell equation, divergence of D equals charge density, in integral form. Both the differential form and the integral form are known as Gauss's law. Giving these two equations a specific name, namely Gauss's law, is appropriate because they are both of fundamental importance but also very handy in problem solving. Gauss's law is the convenient starting point for the calculation of electrostatic fields that arise from charge distributions with a high degree of symmetry. In particular, those charge distributions can then be surrounded by a symmetric virtual Gaussian surface. For example, in the case of spherical symmetry, an imagined sphere, or in the case of cylindrical symmetry, a visualized cylinder, a virtual cylinder. In many such symmetric problems, Gauss's law of electrostatics then provides a convenient means of determining the electric field with a minimal mathematical effort. Importantly, it often permits a straightforward solution of the standard problem of electrostatics, namely the determination of the electric field at a point of interest. Let us see how to transform the integral form of the first Maxwell equation into its differential form and vice versa. And finally, how to calculate electric fields using Gaussian virtual surfaces. Since the four Maxwell equations are the accepted foundation and postulated base of electromagnetism and of general validity, one can always start by writing one of those postulates. In this case, we write down the first postulate: the divergence of D is equal to the volume charge density at a particular point in space R. This postulate, like the other three Maxwell equations, assumes implicitly the validity of vector calculus. Therefore, the full strength of vector calculus can be brought to bear. And we do this here by applying the divergence theorem. The divergence theorem relates a surface integration with a volume integration. In words, one can say that it represents the fundamental truth that the net flux through the surface of a volume has to equal the flux that is generated inside this volume by sources. If we consider an arbitrary vector field A that is defined in 3 dimensions, we can then also define a closed complete surface somewhere in space and look at the vectors on the surface of that volume. The closed integration over the vectors on the surface of that volume is then given by the surface integral A dot ds, whereby ds is the surface differential. That is the left-hand side of the divergence theorem. On the right-hand side of this theorem, we consider what is inside the volume, and we carry out a volume integration over the divergence of the vector field, which identifies the sources of the vector field, and that's done by integrating over divergence A dv, whereby dv is the volume differential. So the left-hand side of the theorem tells us what goes through the surface, and the right-hand side tells us what is created or possibly disappears on the inside. That is the meaning of the divergence theorem. Since this theorem is of general validity and true for any vector field in vector calculus, it can certainly be applied to electrostatics. The red box emphasizes a direct translation of the divergence theorem into electrostatics. The volume integration of the sources of the electric flux density D, divergence D, is on the left, and because of the theorem, this has to be equal to the closed surface integration over the vector field D itself as it penetrates through the surface, d dot ds. Now we apply the first Maxwell equations and replace divergence D with the charge density rho v. Carrying out the volume integration over the charge density rho v gives us the total charge Q of v, the total charge inside the volume v. The equation indicated by the red bracket, which relates the flux penetration through a closed surface to the total charge, the total net charge inside that surface, is known in electrostatics as Gauss's law. In brief, it states that the electric flux integral over the entire surface of a closed volume equals the net electric charge inside. Let's visualize Gauss's law. Let's imagine we have some source charges here, maybe represented by the styrofoam, an odd distribution. One thing we know about these source charges: each of those source charges is the starting point of a field line, which we might represent by these sticks. There's one field line coming out. They're all emanating out in a radial fashion, diverging away from each other. Another source charge here, another field line coming out, and so on. So this is how we imagine a source charge distribution with lots of field lines going out. What can Gauss's law tell us about this? Well, in the case of Gauss's law, the first thing we have to do, we have to imagine a virtual imaginary surface that goes all the way around, that is closed. And we might represent that by this plastic bag. Let's put our distribution in the plastic bag and see what that looks like. Now we've got a virtual Gaussian surface closed, and what we can do now, we can go over this surface and see where the field lines come through. There's one here, there's one there, there's one there, and another one there, here. So you can see if we now count these field lines, we get a measure of the point charges, the source charges inside, because each field line on the surface connects to a source charge on the charge distribution. So it's obvious that the surface integration over all these vectors has to be related to the number of source charges inside. The surface integration of the vectors over our virtual plastic bag Gaussian surface tells us what happens inside this surface, tells us about the number of charges, the number of sources in the charge distribution. The cartoon illustrates the situation for the simple case of one positive point charge. Surrounding the point charge in red with a yellow virtual surface, the Gaussian surface, allows us to identify the field vectors on this surface. If we now integrate over all those field vectors poking through the yellow surface, we obtain a positive quantity, and that positive quantity is representative of the positive charge inside. Let us go through this application formally and apply Gauss's law in integral form to a single point charge, shown here on the left. In order to apply the law, we define a virtual Gaussian sphere indicated in dashed, and on that virtual surface we have a differential surface element ds. Such a surface element exists at any place on the surface, and also at this point in space there will be a field vector d. Since the charge inside the virtual sphere is positive, the field vectors radiate outward. So both the electric flux density and the electric field strength point outward, and they are parallel to the r unit vector of a spherical coordinate system that has its origin in the position of the charge little q. This means mathematically that the scalar product of the two r unit vectors r head dot r head gives a scalar 1. This greatly simplifies the surface integration. The integrand now is simply a scalar product of the magnitude of the field strength on the surface times the total surface area. The total surface area of a sphere is 4 pi r squared. And since all points on the surface of the sphere have the same distance to the origin where the source charge is located, the field strength, the magnitude of the field, is constant, and the integral becomes simply d, the magnitude of the field, times 4 pi r squared, whereby r is the radius of our virtual sphere. Let us look at our simple example in a different way and ask the question: what is the net balance of sources and sinks inside the yellow Gaussian surface? We can work this out by applying the divergence probe, divergence of d, nabla.d, and integrating over that divergence of d over the entire volume of our yellow sphere. The answer is obvious. Clearly, there is only one positive point charge right at the center of the yellow sphere. Let us establish this in the most general three-dimensional approach, which appears complicated but will give us certainly the same result. First, we realize that this simple problem has spherical symmetry, and it is therefore best addressed in a coordinate system using spherical coordinates. This means in particular that the differential volume is given by r squared sine theta dr d theta d phi, whereby r is the radial coordinate, theta the azimuthal coordinate, and phi the polar coordinate. The divergence operator, nabla dot, takes a very complex form, which is shown at the bottom of this slide. The complexity of the divergence operator in spherical coordinates should, however, not concern us, because, as we'll see in a moment, the last two terms are not relevant because of the symmetry of the situation. This is because the field vector only has a component that is parallel to the radial vector. Therefore, only the coordinate dr is different from 0, but the d theta and the d phi coordinate of the field vector are always 0 on every spot on this surface. The last two terms of the divergence operator are therefore exactly 0. With this preparation, we can now solve the integral, the volume integral over the divergence of the field vector inside this virtual Gaussian sphere. The three integrations are written out in the red box. The last two integrations over theta and phi just give a constant factor 4 pi. Integrating over sine theta from 0 to pi is equal to 2, and integrating over phi from 0 to 2 pi is equal to 2 pi. Together, that's a factor of 4 pi. In contrast, the integration in the radial direction looks quite complicated. We see that the integrand contains a partial differentiation and several terms r squared. Two of these terms cancel to give a 1, but what is the integral over d on dr of r squared times dr integrated over r? What is this? Mathematics alone cannot provide the answer to this question, because mathematically d is just defined as a vector field. Experimental physics, however, tells us what the structure of this vector field is. It does that through Coulomb's law, the observations that are comprised in Coulomb's law. Observations with the torsion scale, as shown on the left, and comprised in Coulomb's law, tells us that the electric field is proportional to the magnitude of the charge, and it is inversely proportional to the square of the distance from that source charge. This means the radial component of the vector field dr, which is equal to permittivity constant times er, is proportional to charge divided by distance squared, r squared. Consequently, in our integral, we can replace the dr with q, which is the charge at the center of our virtual Gaussian sphere, divided by 4 pi r squared. Substituting for dr simplifies the integral. Q on 4 pi can be moved out because they are constant, and the integrand is now a differentiation of 1. Integration over a differentiation gives unity. We have therefore obtained the result that we initially expected. The volume integral over the divergence of the vector field inside the virtual Gaussian sphere is equal to the source charge q at its center. We have in fact shown that the experimental Coulomb law is equivalent to the postulated Gauss law, the first Maxwell equation. This becomes clear if we summarize our consideration once more in the equation at the top of this slide. On the left we have d, the field, times 4 pi r squared. That is mathematically the same as the surface integral over d ds. This surface integration is the same as the volume integration over the divergence of d, because of the mathematical divergence theorem. The volume integration over the divergence of d inside the sphere tells us about the net sources in that sphere. Since we have defined this problem, we know that the only source inside is a positive point charge q. And the experimental facts comprised in Coulomb's law tell us that such a point charge has a field that is proportional to q on r squared. In other words, combining experimental observation about electrostatics with vector calculus shows that Coulomb's law, the experimental physics law, is equivalent to Gauss's law, which we have postulated as the first Maxwell equation. This postulate is therefore an appropriate base of electromagnetism, since it reflects the reality of Coulomb's law. Strictly, we have only shown this for a point charge. However, since the principle of linear superposition applies in electrostatics, an assembly of many millions of point charges can be treated in principle in the same way. So instead of using Gauss's law as the first Maxwell equation, one could instead postulate Coulomb's law together with the principle of linear superposition, and a similarly sound basis of electromagnetism would result. The somewhat complex considerations are also important because they show also that the differential and the integral form of Gauss's law are equivalent and can be equally used as defining equations for electromagnetism. We can see this in the top equation, which only holds if the divergence of d is equal to the charge density ρ, which is the differential form. However, due to the divergence theorem of vector calculus, the volume integral of the divergence of d is equal to the surface integral over the closed surface around this volume, and that is the integral form of Gauss's law. We can summarize that Gauss's law represents the physics reality that we know from observation of electrostatic phenomena, and in particular from Coulomb's law, correctly. The differential form and the integral form of Gauss's law are equivalent. They can be readily related using the divergence theorem of vector calculus. This means that either form, the differential or the integral form of Gauss's law, can serve as one of the four fundamental laws, one of the four fundamental postulates of electromagnetism. The integral form shown here is particularly useful in solving many important electrostatics problems.